The next talk is from Hudobivnik from University of Hanover. And Blatz, you can share your slide. Okay, thank you. And the title...
Can you see and hear me?
Yes, thank you.
Good.
The title is NURBS-based geometries, a mapping approach for virtual serendipity elements. So please.
Thank you very much for the nice introductions. I'm Hudobivnik from the Regarses group in Hanover, and I will be talking about a general mapping approach for serendipity elements. So the current state of virtual element method is that generally integration is performed on a physical space and on the straight edges, even for higher order. So today and the last 2 days, we saw that there is a big trend to shift to curved edges. We had some talks about this, and we also did together with Eduardo and Belao de Vega some contact on curved geometries. But today our goal is to extend this to integration on a regular reference simple space, and then we can map to any curved geometry, not just this one singular edge. So first, let me start with some basic governing equations. So we have a finite strength form of momentum balance equation, so the divergence of sigma plus alongside with the Neumann and Dirichlet boundary conditions. We define a homogeneous compressible isotropic hyperelastic model, a Nail-Hooke strain energy function, which is given here. It is a nonlinear function over the element domain. And we have to construct the deformation gradient, so our only degrees of freedom will be displacement in this case. And then we have to integrate the total mechanical energy on the whole initial domain. So labeled with 0, omega 0, but now our idea is to introduce a reference domain, which is labeled as omega r, and we can integrate everything on this reference simple square domain with straight edges, and then we map to some initial domain, and then this initial domain can then deform. Now there's several mapping functions possible. We can have polynomial basics function, which map from the square of 2 times 2 to some arbitrary square. These functions are very simple. They have some disadvantages. They cannot describe accurately some geometries like circles. But the alternative is also NURBS functions, non-uniform rational basis plane functions. These are a bit more complicated to define, but they're used very commonly in 3D generating softwares and also in isogeometric analysis. And just to show you some examples, we have a square mesh, and we can map it with NURBS, for example, to a perfect disk. And with the polynomial to a disk, but it will not be a perfect disk anymore. And we will focus more on the NURBS in this work. Now I will go quickly through the virtual element method, since everybody already should know these basics. So we have a field variables of displacement called UH. They are defined. They are not known inside the element. So here we can see the blue lines. These, for example, are they're only known at the edges. And then we need to split these field variables to the projected part and the error part. The projected part will be labeled as U pi, and these are represented by this orange function here. This is a polynomial function of second order. So we will, these projection functions look like this. We have 1 x epsilon x times epsilon x square multiplied with the matrix coefficients, and then when we multiply those two, we get the projection U pi. Now to find these coefficients A pi, we have to construct a Galerkin type projection of the gradients together with the projection for the displacements, and we multiply the differences with the test function U pi, which is again a projection function, but it has the different coefficients AP, not A pi. Then we can separate the projection part on the left side labeled as G, and everything to do with the nodal degrees of freedom we put to the right side labeled as B. And from this G and B, we can derive the matrices G and B, and finally get the parameters. Now the G is first integrated over the volume, but we can shift this by using the divergence theorem on the integration over the edge of the element. And then we are left with some divergence term and the constant displacement. So we have to integrate the projected displacement area, but we can shift again to this by using the divergence theorem to the edge. And we obtain the final form for the G matrix, which is then obtained by deriving this scalar G with respect to AP parameters and AP parameters. So this is all done in the code. That is why I'm showing all these derivations. Now we do the similar for the B side. So for the right-hand side, we shifted to the integral over the edge, and we are left with the integral of the UH multiplied. But as you know, the UH is not known on the volume. So we have two options. We can introduce internal degrees of freedom, internal moments, M, or we can use the serendipity concept and replace the integral of UH with the integral of UC, and UC can be also a projection function with the third set of coefficient AC here. And we will use this, and we can then integrate UC over the area or over the edge again. Now we also define the right-hand side by deriving this scalar B with respect to coefficients A. Now the serendipity part is shortly described here. We have this UC, which we have to define and by performing a Galerkin type projection. So we have this function U, that is U pi in this case, and we multiply it with UC minus UI, which are the nodal displacements. So we just have to sum this over every node. And in similar manner, we construct the left and right hand side, and we can solve the system of equation given here. But for more details, you can see some of the works of us or Berardo da Vega. Now our task is, so as I said, we will have to integrate on the reference configuration. So we define the matrices G and B in the reference configuration. But for this, we can use the Nansen formula, or we can express the normal, which is given here, or curve geometry. The normal N0 can be then expressed as a function of the reference coordinates. That is one option. Or we can calculate the normal NR and then use the transformation matrix F0, this mapping, to shift it to the curve geometry. So both of these ways will yield the final same result. And then we can use the numerical integration scheme, so Gauss integration point with multiple points on this straight edge here, and we will obtain the correct projection parameters. Now we have to construct the total strain energy of the element. This is a contribution, the total energy is a contribution of each element energies. So we have consistency part, which produces rank deficient tangent, and then we have to add stabilization part to it for completeness. The consistency part is not in cares, but the integral of the strain energy of the projection instead of the true displacement. And once we have this inner energy of the element, we can derive this energy with respect to all the degrees of freedom U to get the residual. And then we repeat the differentiation again. We differentiate the residual with respect to degrees of freedom U to get the tangent matrix. So this is done with the automatic differentiation technique of the HGen software tools. So we don't have to code this, we just have to code the energy. Now we have to integrate the energy. So here I have shown 3 ways how to integrate. So we have the standard elements. These are the first 2. We can find some Gauss curve geometry, or on the straight edge geometry on the triangle. And generally, we have been using the straight edge elements, but we will also show a curved edge elements and compare them both with this our projected formulation, which is at the end here at the C. So we can find the Gauss points over each of the triangle of a submesh of the element, and we send this inside the element code and integrate at that points. Of course, on just have to multiply with the transformation Jacobian. Now for the stabilization part, as you know, we were using the energies for the low order element for our works, but in this case for higher order, we will be using the error of the UPy at nodes. So the standard stabilization, which performs very well in this case. And then again, in the similar manner, we can define the residual and the tangent matrix of the finite element, and then we can sum both residuals and tangents up, and we got the tangents of the whole virtual element. Now let's go to some examples. So first example is a simple patch test. We have disk. Here I have shown some concave mesh with 5 elements, and this disk, this is sent inside the element, and then it's mapped to a circle. We load this disk uniformly with normal load, so we have a uniform compression. And if I show some results here, so the first one is the standard virtual element with straight edges. So second order serendipity virtual element, we can see constant stresses as we expect. Then we have the same element, but integrated on a curved edge instead of a straight edge. And you can see it produces some big oscillations ranging into some 10% stress oscillations. And the last we have our mapping element. This one still produces some oscillation of stresses, but they're much lower orders of magnitude. They're just few percent of stress oscillations. And below you can see for structured mesh the same. And here you can see that the results are basically all same. There's some oscillation on a 4th digit. Now the next example is a Cook's membrane test. We have a reference domain which is 1 square, and this is mapped to a skewed geometry of the standard Cook's membrane geometry. We have been using structured quad mesh and Voronoi meshes. And here there are some stresses shown. So the first one is standard serendipity element, and this one with MB is the mapped. And you can see the stresses, they are matching in all the cases for all the meshes. It's a convergence study of all these models. And we don't see much difference in this case because they're more or less all performed on a straight-edged formulations. But let's go to the next example, which is a C profile. We have inside the C profile, we have this curved geometry. So our reference mesh is 10 squares of 1 times 1 size, which are then mapped to this curved geometry. And then we have a force applied here. They're pushing it apart and trying to open it. And if we show some stresses with the huge deformations, we can see here the fine film solution, and all the other formulations give the same result. But if we check some convergence study of an error, we can see in this case that the integration on a curved geometry, also the standard Vim and our mapped Vim is here. So this gives much better results than integrating on a straight edged element. Now I have the 4th example. We have a quarter of a thick walled cylinder by a reference configuration of 1 square, and then we map this to an elongated curved domain. And again, we have loaded from below, we pushed towards the left, and you can see again we have good match in stresses. And in this case, we also get slight improvement when we integrate on a curved geometry instead of a straight edge geometry, but the difference is not so big as in the other case. In this case, Voronoi performs slightly worse, but this is also a well-known fact. Now I would like to conclude and just the final remarks. So we have shown that the serendipity virtual element scheme for general element shapes undergoing finite elastic strains was suitable to use. A general mapping technique was developed that allows to deviate from the assumption of straight edges of higher order elements. We have used the NURBS basis functions for mapping, but one can use also other functions. We have tried also polynomial, and projected formulation turns out to perform in general better to the straight edge formulation. And although in some cases the results were same as the curved geometry of the standard VM, we have shown that on the patch test, the standard VM produces some oscillations, while R also performs some oscillations, but they're much lower. And this is something we still have to work on. And with this, I would like to conclude my talk.
Okay, thank you, Blatz.